Hey everyone, and welcome. Today, we're jumping into a really cool piece of geometry, the areas of parallelograms and triangles. And you might be surprised to find out how one single, simple idea links these two shapes and basically unlocks a whole new way to solve problems. So let's get right into it and master this together.
Before we get into the theorems and proofs, it's pretty wild to think about why we even study area. It wasn't just some abstract idea a mathematician dreamed up. It all started with a really practical problem, farming. Think about it. How would you divide a field fairly between people without understanding area? You just couldn't. This shows us that geometry was born from a real-world need for order and fairness, and that idea is just as important today.
And that basic need to understand space, it never went away. Whether you're an architect designing a building or a developer creating a video game, the concept of area is literally everywhere. So today, we're going to build on that ancient foundation and really get a grip on the mathematical principles that are still so critical in our world. So, here's our game plan. First, we're going to nail one core idea that everything else is built on. Then, from there, we'll unlock two super powerful theorems, one for parallelograms and one for triangles. And of course, to make sure you've got this down cold, we'll wrap up with a quick summary and a practice test to get you ready for anything. Let's get started.
Okay, everything, and I mean everything we're about to learn today comes down to this one simple but powerful concept, what it means for shapes to be on the same base and between the same parallels. If you get this, the rest is going to be a piece of cake.
First up, let's talk about the same base. Honestly, it's as easy as it sounds. Two shapes are on the same base if they literally share a side. You can see in this picture how both of these figures are built on that exact same bottom line. That's our first condition. Simple enough, right?
Now for the second part of the puzzle. Between the same parallels. This just means that all the top corners, the vertices opposite that base we just talked about, all sit on one straight line. And that line is parallel to the base. Think of it like a sandwich. The base is the bottom slice of bread, this top line is the top slice of bread, and the shapes are perfectly squished in between. That's condition number 2. So here's the most important part. Both conditions have to be true at the same time. On the left, you see the perfect setup. They share a base, and their top points are all on a line that's parallel to it. But on the right, you see the common mistakes. In one case, they have different bases. In the other, the top corners don't line up on a parallel line. Keep this visual in your head, because it is the absolute key to using the theorems we're about to cover.
All right, now that we've got that core idea down, let's use it with our first major theorem. This one is all about parallelograms, and it's a total game changer because it lets us solve area problems without even needing to know the height.
And here it is. The theorem states that if you have two parallelograms, or even more, that meet our two conditions, same base, between the same parallels, then their areas are guaranteed to be equal. It doesn't matter if one looks really stretched out and the other one is more slanted. Their areas will be exactly the same.
So how do we actually know this is true? Well, the proof is actually pretty cool and visual. Check out the setup on the slide. We've got two parallelograms on the same base. Now, look at those two little triangles on the ends. The big secret here is that those two triangles are congruent. They are identical copies, which means they have the exact same area. So think about it. The first parallelogram is made up of that middle shape plus the triangle on the left. The second parallelogram is the same middle shape plus the triangle on the right. Since the two end triangles have the same area, the total area of both parallelograms has to be the same. We've basically just slid an identical piece from one side to the other. Okay, so now that we've got this powerful rule for parallelograms, we can take it one step further. As you're about to see, the logic we just used works perfectly for triangles too. And it all starts with one really simple observation.
So let's just think for a second. What happens when you draw a line from one corner of a parallelogram to the opposite corner? You split it into two triangles, right? So if we already know something important about the area of the whole parallelogram, what can we figure out about the triangles that make it up?
And here's the connection, laid out perfectly. That diagonal line splits the parallelogram into two triangles of equal area, which means the area of just one of those triangles is exactly half the area of the whole parallelogram it came from. This little fact is the key that unlocks our next big theorem.
And there it is. Just like with parallelograms, if you have two triangles that share the same base and are between the same parallels, they have to have the same area. Why? Well, because we know each of those triangles is exactly half the area of a parallelogram on that same base,
And since the parallelograms would have equal areas, the two triangles must have equal areas too. See, the logic just flows perfectly from one to the other.
Okay, we've covered the main ideas and the two huge theorems. Now it's time to make sure that knowledge is locked in. We'll do a quick summary of the rules, and then we're going to put your understanding to the test with some real exam-style questions.
So if you remember nothing else from today, remember these things. First, always check for the two conditions, same base and between the same parallels. Second, if you meet those conditions, parallelograms have equal areas and triangles have equal areas. And finally, never forget the link between them. A triangle is half the area of a parallelogram if they share a base and parallels. That's the whole chapter in a nutshell.
All right, time to put what you've learned to work. We're going to go through a few sets of questions, starting with the easy stuff and then working our way up. I'll put the questions up, you just pause the explainer and solve them at your own speed. Ready? Let's start with the easy ones.
Here are the first 10 questions to check your basic understanding. Go ahead and hit pause now and work through them.
Awesome work. Okay, let's ramp it up a little. Time for some medium difficulty questions. These will ask you to apply the theorems in slightly more complex ways.
And here are the next 10. You'll see some proofs and a bit more applied thinking here. Go ahead and pause and give them your best shot.
Okay, this is it, the final challenge. These questions are designed to really make you think and maybe even combine a few different ideas from geometry. Don't worry if they look hard. They're supposed to be. Just give them your best effort.
All right, here's the final set. These are definitely tricky and will really test how well you can combine these concepts. Don't get discouraged if they take a while. My advice, draw the figures out and really think through the logic step by step. Go ahead and pause now and see how you do. Fantastic work today. Seriously. We went all the way from the ancient origins of area to solving some pretty tough geometric proofs. You've built a really solid foundation. The only thing left now is practice.
And I want to leave you with this idea about the incredible mathematician Srinivasa Ramanujan. He found real joy in just learning and discovering new things. Math isn't always about just getting the right answer. It's about that aha moment, the excitement of finally understanding why something works. So keep practicing, stay curious, and try to find that joy in mastering these challenges. You have absolutely got this. Thanks for tuning in.